Hello everyone. Today we will be learning about information retrieval using semantic-based search with the help of algorithms. In this presentation, we are going to understand how the web search has evolved from simply matching words based on structure to actually understanding the meaning behind those words. We will now look at how traditional search works, what are its limitations, and how the semantic web improves search by adding meaning and relationship to data. So let's begin by first understanding what syntax actually means. Hello everyone. Syntax refers to the structure or format of the data. In simple terms, syntax is about grammar rules and how a data is written. It checks whether a sentence is grammatically correct, but it does not understand the meaning of the sentence. For example, dog bites man, and the second sentence is man bites dog. Both sentences are grammatically correct, but their meanings are completely different. Syntax only checks whether the sentence follows the correct structure. It does not understand who is doing the action or what situation actually means. This is how traditional web systems mostly work. They look at the structure and keywords and not the meaning. Now, let us move to the next main important concept, semantics. What is a semantic? Semantic refers to the meaning of data. While syntax focuses only on the structure, semantics focuses on understanding the context and meaning. In real language, we often have homonyms and homographs, words that look or sound the same but have different meanings. For example, the word train. It can mean a mode of transportation, or it can mean to teach or practice something. So, if someone says, I love riding on trains, we understand from the context that they are talking about the transportation. But if someone says, I train every day, it means practicing or exercising. This understanding of context is what semantic provides. Computers traditionally struggle with this because they only match keywords. That's why semantic understanding is important for improving search systems. Now that we have understood syntax and semantics, let us see how the World Wide Web actually works. When we type a website, for example, www.youtube.com into the browser, several things happen behind the scenes. First, the browser sends a request using HTTP, which stands for Hypertext Transfer Protocol. The URL acts as the address of the website. The request goes to a DNS server which converts the website name into an IP address. Then the server sends back the data in the form of HTML, CSS, and JavaScript files. HTML provides the structure of the page. CSS provides the styling and design. JavaScript provides interactivity. Finally, the browser renders the page so that we can see it. Search engines also work in a structured way. They use crawlers to collect web pages, they use indexers to store keywords, and they use ranking algorithms like PageRank to decide which pages should appear first. However, traditional search engines mainly rely on keyword matching, and this leads us to a major problem. Traditional search engines work mainly based on keyword matching. For example, if we search for the word apple in a search engine, it might show Apple the fruit or Apple the technology company. This happens because the system matches the keyword, but it does not understand what the user actually means. There are three major issues. First, ambiguity. One word can have multiple meanings. Second, the synonym problem. For example, car and automobile mean the same, but a keyword based search might treat them as different. Third, lack of context understanding. The system does not understand user interaction. Because of these limitations, traditional search sometimes gives irrelevant results. This is exactly where semantic web comes into the picture. The semantic web helps computers understand relationship and context and not just the keywords.
So far, we've talked about what syntax is and what semantic means. Now comes the interesting part. What happens when you take that idea of meaning and apply it to the entire World Wide Web? So that's exactly what semantic web is. It's a vision for a smarter web, one where data isn't just sitting in documents for humans to read, but is structured in a way that machines can actually understand and reason with. Think about the web as it is right now. So it's essentially a massive collection of pages, which includes text, images, and links. A person can open a page and understand what it's about, but a computer, it just sees code. It can find the word Paris, but it doesn't know that Paris is a city that is in France or that France is a country in Europe. It has no context. So the semantic web fixes this by organizing data into structured relationships. So instead of just linking pages to pages, we link facts to facts. So a machine doesn't just see the word Paris. It knows Paris is a city is a place, and that place has a population and a location. So now semantic web uses three core technologies to make this happen, and we are going to go through each one on the next few slides. They are RDF, OWL, and Sparkle. So let's start with RDF, which stands for Resource Description Framework. The name sounds technical, but the concept is actually very straightforward. So RDF stores information as triples. A triple is just a three-part statement made up of a subject, a predicate, and an object. You can think of it like a very short, structured sentence. So look at the example on the slide. So we have blueberry muffin is a baked good. That's one RDF triple. The blueberry muffin is a subject. It's a thing we are describing. Is is the predicate. That's the relationship, the verb connecting the two. And baked good is the object. It's what the subject connects to. So now here's something important. In RDF, every subject and object gets a unique web address called the URI. You can see them in the diagram as those URL style identifiers. The reason for this is to avoid confusion. There are millions of pages on the internet that mention the word muffin, but this URI points to one specific unambiguous concept so that no two things share the same URI. And when you chain many triples together, which has like hundreds or thousands or millions of them, you build what's called a knowledge graph, a giant web of interconnected facts that machine can navigate. So RDF is great at storing individual facts. But what if we want the system to reason, to automatically figure out things it wasn't directly told? That's what OWL is for. So OWL stands for Web Ontology Language. An ontology is basically a formal map of a subject area. It defines all the categories in that area, how they are organized, and the rules that govern them. So look at the hierarchy on the slide. At the very top we have thing. Under that is food. Food branches into drink and baked good. And under baked good we have chocolate chip cookie, blueberry muffin, and croissant. Now here's where it gets powerful. Suppose I only told the system one fact. Blueberry muffin is a baked good. Using the OWL structure, the system can automatically reason. If a blueberry muffin is a baked good, and a baked good is a food, and a food is a thing, then a blueberry muffin must also be a thing. The system figured that out on its own just by following the chain. This is called logical inference. This is exactly the kind of reasoning that powers tools like Google's knowledge graph. When you search for a person, Google doesn't match your words to a page. It understands that the person's relationship, their profession, the films they appeared in, the awards they won. All of that comes from ontology structures like OWL. So now we built a knowledge graph with RDF and organized it with OWL. Now the question is, how do we search through it? How do we ask a question and get a meaningful answer back? That's the job of Sparkle. So SPRQL, pronounced Sparkle, is the query language for the semantic web. If you ever heard of SQL, which is used to query regular databases, Sparkle is the same idea but designed specifically for RDF knowledge graphs. So look at the example on the slide. The query is asking me to find every item in the knowledge graph that is a type of muffin. The system then scans the entire RDF graph, follows the ISA relationships defined by the OWL ontology, and returns every match. So in this case, it finds blueberry muffin and brown muffin because both of them have that is a connection leading back to muffin. So what makes Sparkle really different from a regular keyword search is this. It doesn't look for matching words. It looks for matching relationships. So even if a document never uses the word muffin, if the data graph connects it correctly, Sparkle will still find it. Now let's put everything together and see what actually happens when someone types a query into a semantic search engine. This is the full pipeline from the moment you hit search to the moment results appear. So stage 1 is knowledge graph construction. Before any search can happen, the system needs its data. So in this stage, real world facts are converted into RDF triples and stored in a knowledge graph. This is done in advance, which is the foundation to the whole system which it runs on. Stage 2 is query parsing. You type something like cheap laptops for students. The system first processes your input. It breaks the sentence into individual tokens, removes filler words like for and the, and extracts the meaningful keywords like cheap, laptops, students. Then stage 3, which is concept mapping. Each keyword is now matched to a concept in the ontology. Laptops might map into the concept portable computer. Students maps into learner. This is the step where the words you type get translated into structured meaning. This is where the syntax officially becomes semantics. Then stage 4, which is query expansion. The system now broadens the search by including related concepts from the ontology. So laptops might also pull in notebooks and portable computers because the ontology knows they are connected. This way, the search captures everything relevant, not just exact matches. Then stage 5, which is graph traversal. With the expanded set of concepts, the system traverses the knowledge graph to find the matching patterns. It uses graph search algorithms like breadth first search. starting from a node and expanding outward, following relationships until it finds everything that fits. And then stage 6, which is Sparkle query generation. So finally, all these towers, concepts, and relationships are converted into a Sparkle query that gets executed against the knowledge graph to pull the actual results. The system built this query automatically based on everything it understood, and you never had to write a single line of it. And that's the full picture. Every time a search engine seems to just get what you meant, even when you didn't phrase it perfectly. This is the pipeline running quietly in the background. Syntax gives us the words, semantics gives us the meaning, and the algorithm connects the two.
As we explore the advantages of semantic search, let's focus on how it enhances our interaction with information. First, consider how this system understands what you mean, not just what you type. This reduces ambiguity significantly. For example, when you search for faculty, it recognizes you might mean professor, providing you with more accurate results. Next, the system excels at finding related concepts even if they go by different names. Searching for AI will also bring up machine learning. This capability improves recall, ensuring you uncover all the relevant information. Moreover, semantic search follows a map for logical reasoning. It knows that a muffin is a type of baked good. So, if you asked all baked goods, muffins are included. This logical reasoning helps in uncovering hidden answers. Finally, think of it as exploring a web rather than scrolling through a list. You can seamlessly click from one concept to another, like moving from a professor to their course, then to the room it's held in. These advantages make semantic search not just a tool, but an intelligent companion in your information retrieval journey. As we reach the conclusion of our video, let's take a moment to wrap up what we have discussed and understand the broader implications of semantic based navigation systems. Firstly, it's important to remember that syntax and semantics play distinct roles. Syntax provides the structural rules, essentially the framework, while semantics gives the structure meaning. Think of syntax as a skeleton and semantics as a life that animates it. The traditional World Wide Web was primarily focused on documents, lacking the capability to provide machine understandable meaning. This limitation has been addressed with the help of the semantic web, which utilizes technologies like RDF, OWL, and SparkQL. These tools allow us to structure data in a way that machines can interpret and use intelligently. Semantic based navigation leverages these structures to enhance how we retrieve information by employing knowledge graphs, ontology reasoning, and graph traversal algorithms. Also, logical query processing is involved. We are able to shift from simple keyword searches to intelligent semantic reasoning. This means more accurate and relevant results tailored to the context of a query rather than just the words used. Finally, the flexible up of this approach allows it to be applied across various workflows, making it a powerful tool in diverse fields, whether you're in academic, business, or any other sector. Semantic based navigation can transform the way you access and interact with information. Thank you.